Okay, so now if I consider the right half plane 0, then what should be my phase margin? So what is phase margin after compensation? So what is UGB? What is omega UGB? So whatever the pole frequency multiplied by your loop gain. Okay. So omega P2 dash multiplied by I'll just call it DC loop gain. Okay, which is your omega P2 dash beta naught. Correct. What is DC gain? So let's assume beta equal to 1. So by the way, why do we always assume beta equal to 1 when you compensate? Because that's the worst case. Because loop gain is maximum at beta equal to 1. So what happens? Your UGB will be maximum. So if you compensate for beta equal to 1, if beta we know it's always less than 1. So let's say beta equal to half, your UGB will be reduced by half. So you have compensated for a 2x frequency. So at half frequency, obviously it will give you better margin, phase margin, because now your two poles are, the second pole is further away from your UGB. So if you let's say approximated 1.7 times, now it will be 3.4 times away. So that's why we always compensated for beta equal to 1, so that it's compensated for all values of beta as long as beta remains less than 1. But if you implement a circuit which has a beta greater than 1, which means instead of resistor divider you have a feedback amplifier, okay, in that case you have to make for maximum beta, compensate for that. But that is a very rare circuit you design for. Regulators are designed with a feedback resistor only, where beta is always less than 1. Okay. So what is A naught? GM2 RO2 correct. What is omega P2 dash? 1 over RO2 GM3 R out CC. So what is your omega UGB? So this. So UGB is independent of your output resistance, only depends on GM2. Yeah, sorry. Okay. So if I want to maximize UGB, all I need to do just increase the transconductance of your first stage. And so what is your phase margin? And where was your 0? Omega z, right half, right half plane 0. What was the frequency of that? GM3 CC. So what is the phase margin? (180 minus tan inverse omega UGB over omega P2 dash minus omega UGB omega P1 dash P2 dash minus you have a right half plane 0. If you have a left half, it will give you positive, but so the right half plane 0 is the worst thing you can have in your loop. The reason is it drops the phase and increases the gain. So, it will phase margin is very, I mean it's basically worse than a pole, because pole will drop the gain even though it's reducing the phase, but reducing the gain also. But this guy is reducing the phase and increasing the gain. So, you will not cross 0 dB early, it will basically shift at higher frequency and it will make it even worse. Over omega z. And what is the phase shift from this first pole? We know that, so it is 90 degree. So, I can say 90 degree minus tan inverse, and what is omega UGB? GM and omega P2 dash, what was the frequency? GM3 by we had C so this is the with the assumption that Cc is larger than your CO1 CO2, okay. But if you don't assume that, you have to write the whole thing minus tan inverse. So, omega UGB again write the GM2 over Cc over GM3 over Cc, correct. So, if I want to reduce the effect of, so which means phase shift due to right half plane 0, let us say call it phi z, is nothing but minus tan inverse GM2 by GM3. So, if GM3 is much larger than GM2, then phi z is 0. So, this is the one way you can reduce the effect of your right half plane 0 by making sure your output stage GM is much larger than input stage GM. Then you can reduce the effect without doing anything actually. You don't need to put the series R and all those. But ensuring this is not easy. The reason is, I mean at higher load current obviously this GM3 will be very large. So, you won't see the effect of right half plane 0, but at very light load, let us say 0 load, we took the case, it is quite possible that your output stage GM may be less than your input stage GM. In that case, your right half plane 0 will kick in and will start your reduce your phase margin. So, that is why we always prefer to get rid of this by using that adding that series resistor. Okay, any questions? Okay. Yeah, that is what I am saying.
The lightest load current.
If you ensure that GM2 by GM3 ratio is much low, let us say 0.1 or so, let us say GM3 is 10 times of GM2, then the phase contribution will be very low with this. So, if you ensure that at a lightest load, then at highest load that will be even better. So what I am saying, but the problem here is actually you want to keep the GM2 also high. You cannot keep it very low due to offset reasons. When we talk about the offset, then we'll look into that. So if your amplifier has a very low GM, your input referred offset will be very large actually. Okay, because any mismatch in the current will get reflected as a large change in the voltage, because we know GM is delta I out over delta V in. Okay. So if your GM is very low, that means a small change in the current will cause a large change in the input voltage, and that is why input referred offset is large if GM2. So most of the time you deliberately design it for higher GM. Other thing is the UGB you have to consider, and UGB is a function of your first stage GM. So for a one particular UGB you have designed, then again you have to make sure. So which means you have to always have some minimum current at the output stage to ensure a higher GM. So that will always come at the cost of your current consumption. So you can always ensure that, but there is a penalty of your power consumption. And most of the time we care about the power. So we try to find a ways where you can basically get a better performance without increasing the power. So that's why the having that series resistor is a better option compared to by reducing the ratio of GM2 over GM3. And another advantage we already mentioned, that you can cancel the second pole, so you can extend the bandwidth. So that's another advantage. So designing a higher bandwidth becomes more feasible with Miller compensation compared to your dominant pole compensation, and this will further can be improved by cancelling the right half plane 0. So we'll continue with the right half plane 0. So one technique in order to mitigate the effect of your right half plane 0 was to choose the GM ratios properly. Okay, so GM3, if we choose higher than GM2 or much higher, let us say 10 times also. So what would happen, that right half plane 0 effect will be less, because the contribution for the phase, because that right half plane 0 basically that will be at much higher frequency, and so the contribution in the phase will be less. So your phase margin will be still decided by your dominant pole. Okay. So mitigating so let's go one by one. What was the very first method? Series resistor, nulling resistor, we call it nulling resistor actually. So nulling resistor, so what it does, number one, if you choose RC greater than or equal to 1 over GM2, then what happens? Right half plane 0 will go away or convert to left half plane. Okay. Second method, choose GM3 much higher than GM2. So right half plane 0 is pushed at high frequency and phase margin is correct. Now let's look at third method. Method 3. So if this is GM1 or since we have been calling it GM2, so let's GM2. So this is your Miller cap, okay. Let's say this is your, I'm just drawing R out equivalent, and you have some C out. So we know that, so the current from output to input, if this is VO1 and this is V out, so from V out to VO1, that is causing your Miller effect, correct? Miller effect. And feed forward current which is going from VO1 to V out, that is causing your right half plane 0. Which means if we allow only reverse path and block the forward path, then we can get rid of right half plane 0. How can we do that? And that's what your nulling resistor does. When you put the resistor, what it does, it basically weakens your forward path. I mean, you have a two paths. One path is coming from GM, transistor GM, other path is coming from the capacitor, and you want the GM path to be stronger than your resistive path, correct? So that's why you choose RC greater than 1 over GM. Higher the resistor, weaker that path is. So your output will be mainly defined by your GM. So it will be out of phase, 180 degree out of phase, and the path which is in phase caused by the right half plane 0, that will be weaker. And that's what happens when you put the series R. So which means I have to replace that R with something else and I can block it. What if I do this? Put a buffer in the feedback path. Okay, so buffer has a very high input impedance, output impedance is low, so it will basically block any forward path, and so it will have only this. Let me change the color. So this path is there, but this path is blocked. So no right half plane 0. And this buffer can be implemented with this. This is nothing but, what do you call it? Source follower. Or common drain. Okay. So the impedance looking at the other end of the cap will be 1 over GM. So you might have a 0 due to that GM, but GM you can choose and push it at high frequency. So if you choose the GM in such a way that you can bring it inside and cancel your 0, or you just push it outside your UGB. And your output, what will happen to your output impedance? Comparing this one and this one, will your output impedance change or remain same? It will remain same because you are providing the output signal to the gate. So it will not get affected. But if one is replaced with some A, let's say A gain, then what would happen? So your R out will be boosted by, decreased by 1 over A times. Correct? And what will happen to the Miller cap? In this case, your Miller cap is output stage gain times GM R out. Now you have one more gain stage in that loop, Miller loop. So GM R out multiplied by that A times. So your Miller cap will also get boosted. So that's the advantage if you, instead of buffer, you put an amplifier in the feedback. Then you can push your output pole at higher frequency and the dominant pole at even at lower frequency, which means that will require a smaller cap because your multiplication factor is now increased. Okay. Any other way of yeah, so that's mainly 3 methods. So there is one more method which is not used to reduce the effect of this right half plane 0, but to reduce the effect of this gate cap. So let's say you want to make output pole dominant. So if you want to make output pole dominant, you would like to reduce the cap at VO1. So how can we reduce that? So let's take the case of if output pole is dominant, then, or let me write this way, reducing the effect of omega p1 if omega out is dominant. When I say omega p1, this is omega p1, this is omega p out. Okay, this note. So how can you do that? Which means there are 2 ways. You reduce the gate cap or you reduce the output impedance looking at that node, okay, whatever you call it, R01, R02 or whatever. Okay. So how can we do that? So one way is just insert the buffer. Okay. If I insert the buffer, now this whole thing will go away. No Miller compensation. Okay, and you can use the same source follower. Whether you use a N type or P type, that will depend on how your output signal, the basically bias, depending on the biasing basically, where it's getting biased. How can I reduce the gate cap? So this will become 1 over GM roughly, looking at the source of your output. So your omega P1, if this cap is, let's say, I call it CO2, then becomes GM over CO2. Okay. Which will be much higher compared to 1 over RO2 CO2. Correct? Now reducing. So for the same GM, we know the NMOS mobility is higher compared to your PMOS. So instead of using PMOS, we'll use the NMOS regulator. If you use the NMOS regulator, then the gate cap will be much less compared to your. Okay, but the problem with that is that will be a source follower. So you will not get any gain from the output stage. So your error amplifier, all the gain will be coming from your first stage. So you may require a 2-stage amplifier there, but that is fine. Other thing is, in that case, your so the dropout voltage basically, it requires much larger. It will not work with the lower dropout. So what happens in the NMOS? This is your VDD. So VGS should be greater than VTH, correct? If V drop is, let's say, 100 millivolt, plus minus 100 millivolt. So the source is how much? VDD minus 100 millivolt. So what is the minimum VGS you will require? VGS should be greater than VTH plus VDD minus 100 millivolt, and VTH is roughly 500 millivolt. So VG, so VG required is greater than VDD plus 400 millivolt. That will not work with lower dropout. So your dropout should be more than your threshold voltage, otherwise it will not work. So which means you require to boost the gate voltage. So sometimes what you do, you use a separate supply for this error amplifier. So now I'll just draw the amplifier instead of drawing that whole thing. GM and this will be, let's say, I would just say VDD of if this is your error amplifier, EA is greater than VDD plus VTH. So you take the VDD. If you have already that, let's say on your system you have a power supply of 1.8 volt and 2.5 volt, and output you require less than 1.8 volt, then you can put error amplifier at 2.5 volt and get it worked. So it's not a problem. But if you have a single supply which is VDD 1.8 volt, then what you do, you use a capacitive charge pump and boost that voltage and supply that. And there are a lot of benefits actually with that. So gate cap is reduced. If you want to make the input pole dominant here, then you have to put obviously the larger cap at the output of this. If you want to make the output pole dominant, then again your output impedance you are looking at is 1 over GM now. So you may require to put a larger output cap also. So this is this may be quite useful if you are looking at a very large, or you want to drive a very large output cap. Okay. And there is one more benefit on PSRR. When we talk about the PSRR, then we will see how this benefits more in PSRR, in case of PSRR compared to the this PMOS LDO. So both are used actually depending upon the application. So sometimes even after adding those charge pumps and everything, overall area may be less compared to the PMOS regulator, because these days the mobility factor is not just 2, it's more than 3 or so, 3 to 4 times. So you will get a huge area advantage with this. So even if the, let's say after adding charge pump, the two have a same area, the performance of this may be better than compared to your PMOS LDO in terms of PSRR and all those.